Nathan, glad you joined us. If you just lose the mic, Nathan, that would be good, thank you. Right, okay, so we're just missing Joe and James, so if they wouldn't mind just playing this recording, because it's just a key few bits and bobs I want to hook out. So we're moving on to the next bit, 7.4, where it's more practice of what we were just doing. So if you haven't managed to get as many questions done from the prior lot, I would suggest you leave those and you concentrate on doing these questions, because it's the same skills, but we're just now adding moments into the mix. Okay, so remember we did moments earlier on, and remember a moment is the turning force, and it's the force times the perpendicular distance. Okay, now I think the key thing with these is to get your diagram sorted and to be confident which directions the arrows are going in. If you get the arrows all right, your diagram right, you're giving yourself a fighting chance. Okay, I noticed yesterday when I was marking one of the previous chapter tests, one of you, because you got your diagram wrong, everything was wrong. Okay, I mean, had your diagram been right, your answers were completely consistent with your diagram, but the diagram was wrong, so really you just got no marks. So it's ever so important to get the initial diagram right. So example 7, I don't want to spend too long on it, but I just want to remind you of a few key points. Okay, so we're just trying to here we were taking moments about A. All right, so we've just got to get the perpendicular. So where we've got that weight, it was a uniform rod. Remember, with the uniform rod, the weight is right in the middle. And my suggestion to you is, don't make the arrow for the weight really small like they've done there in black. Okay, make it nice and big. Look at my big purple arrow. I don't think it's so much easier, I think, than to picture the perpendicular distance. So that purple arrow is my weight. Okay, so I've drawn it all the way down, and then I think it's so much easier to see that red horizontal line, which is the corresponding perpendicular distance. Okay, so so that's my first point to suggest you do. I mean, that pink moment is quite easy, because that's literally already at 90 degrees. Okay, that's already at 90 degrees taking moments about A. But so that was my first point I wanted to make on example 7. Secondly, please note how on this particular question we're told that the peg at the top is smooth, so you don't need to worry about any friction up there. So whenever there's any bits and pieces are smooth, forget about friction. But it's a rough surface down here on the floor, and remember, the friction just goes in the opposite direction to any potential movement. So we've got a uniform rod here, and you know, if it was just to slide down off this peg that it's sort of rested against, obviously the bottom bit of the rod would just move to the left, so the friction is to the right. Now I then wanted to so that's all the points I wanted to hook out from example 7. Now in example 8, a couple, well, lots of points I wanted to make here. Okay. Oh, by the way, I meant to say on example 7, because I've taken moments about A, the normal reaction R and the friction were taken out of the equation. Yeah. So when I took the moments on example 7, it was only the weight and the normal reaction up here at N that were part of my moment. So take moments about whatever eliminates the most points. Now, with example 8, I think there are 2 critical points here. Okay, this is the classic ladder question. Okay, so we've got a ladder resting on the floor and against the wall. Okay, and then we're told various information about the weight of the person on the ladder. It's a uniform ladder, I think. I think it's a uniform ladder. Probably, yes. The ladder is modelled as a uniform rod, so that's why the weight is in the middle bit and so on. Now, I really want you to focus on the forces in play. Obviously, the weight of the ladder and the weight of the person on the ladder are just obviously just going straight downwards. You know, we're very familiar with those. Now, please, bottom left-hand corner, where it's hitting the ground at A. The normal reaction is perpendicular to the ground, so that's going straight upwards. If the ladder was to slip, just imagine you're on a ladder, the bottom of the ladder is going to move to the left, and the top of the ladder is going to fall down the wall, it's going to go downwards. So the friction at the ground is to the right, because it's opposite direction to any potential movement. Now, with this particular question, we were told that it was smooth against the wall, so there wasn't any friction. But had there been friction, and I think this crops up later on question 8, had there been friction, that friction would be an arrow going upwards on the wall, okay? And again, just think of it, if the ladder was slipping, the ladder would go down the wall, so the friction is going upwards. So please be very clear about those orange arrows, which were part of example 8, and the purple arrow, which would just potentially have been a force here, the friction, had the wall not been smooth. Now, second point I wanted to make is the bit they go and say down about the problem solving, because I think unless you've actually done a few of these, you wouldn't think of doing this. You would naturally want to take moments about some point on the ladder, okay? Probably A or probably B, maybe C, okay? But it can just be a place in space, okay? So just reading down what it says on example 8 down the bottom right-hand corner, whilst they haven't done it themselves on this question, they're noting that it could be done, okay? So can we just read that bit at the bottom? There are other options for points to take moments about. For example, if you were to take moments about the point where the lines of action of R and P meets, you would eliminate R and P. You'd eliminate R and P from your workings and simplify your calculation. So I think this is ever so important here. So look, if we go and take moments at the top where that green blob is, the green circle at the top, so I've just extended the line for R and I've extended the line for P. If I go and take moments about that point, the perpendicular distance from R is 0 because R is just a big arrow that carries straight onwards, totally upwards forever. Okay, so it's no distance away from that blob. Similarly with P. So say I went and called this point X at the top and I took moments about X, where the green circle is, then I would be eliminating R and I would be eliminating P. Now that crops up on questions 6 and 8. So I think it's crucial that over the next 2 lessons, we make sure we do questions 6 and 8, because I think it's very useful to have this ability to think, do you know what, if I take moments up there in the air, I'm going to be able to take out those 2 forces, and it just makes the whole moment calculation more simple. So it's crucial we do 6 and 8, okay, 2 lessons to do it. So what I suggest we do the even numbers for this exercise, please. All right, so those of you who are a bit shorter for time, just make sure you try and get the even numbers done. Those of you with more frees, start off by doing the evens, but you really should try and go back and fill in the gaps to get the extra practice, okay? But if you only do the evens, you're not missing out on anything, just apart from obviously the additional practice. So I think those were the only points I wanted to make. Yes, I didn't think example 9 added anything to the mix. Bit of Pythagoras going on, a bit of trig, but we're familiar with that. Yes, so we're away. So exercise 7D, please. But let's just do the even. So I'm just going to put number 2 on the board to get you going. So let me just stop the recording. Okay, that's